Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course. States of matter. Today we begin with lecture 6 from the course, but make sure you watch the previous ones before viewing this one. So in the past few lectures, what we have been discussing is about the three states of matter and the factors on which these three states of matter they depend. And these two factors we have discussed in detail. Number one, the intermolecular forces, and number two, the thermal energy. So all the three states of matter, they depend upon the balance between the intermolecular forces and the thermal energy. Now with this understanding in our mind, we are going to move further in the course. We will be talking about the gaseous state of matter, which is going to form the major portion of this course. So we will be having a detailed discussion starting on with this lecture, where we will be just having a brief introduction to the gaseous state, which is going to be really very important for you. So I hope you are looking forward to having a thorough understanding of the gaseous state of matter. So the gaseous state of matter, this is the simplest state of matter, and why we call it as the simplest state is because the forces of interaction between the molecules, they are negligible. When the forces of interaction are not negligible as we have in the liquids and the solids, the structures for the liquids and the solids, they are going to be much more complex. So therefore the gaseous state, this is the simplest state of matter where the forces of interaction between the molecules of the gases, they are going to be negligible. Now quickly let us see the characteristic properties of the gases, which you already know. It is going to be just a brief recap with some important things that I would like to discuss with you. So the first property is that the gases, they neither have a definite shape nor a fixed volume, and that is why, because the forces of interaction between the molecules, they are negligible. The molecules, they are far away from each other, so how is a gas going to have some definite shape or a fixed volume? So the gases, they are going to assume the volume and the shape of the container. Now this is something that I would like to talk to you about when we say that they assume the volume of the container. The liquids, they also do not have a definite shape, but they have a fixed volume. When we talk about the gases, they do not have a volume of their own also. So if, for example, I have 14 gram of nitrogen gas and I put it in a 1 liter container, and I ask you what is the volume of nitrogen, so what is your answer going to be? Well, it is going to be 1 liter. The volume of the container is going to be the volume of the gas, because the gas is going to spread over all the area that is being given to it. Okay, so if I put the same gas, 14 gram of nitrogen gas, in a 2 liter container, the volume of nitrogen gas is now going to be 2 liters. So I hope this is clear, that the gas is going to occupy whatever space is given to it. So the volume of the gas, that may not be given to you in the questions when you are doing your problem solving. It would be the volume of the container that is given to you, and that is going to be the volume of the gas. And sometimes a tricky question can be there, that in the container we have a solid block of wood, say, and that wood is now going to occupy some volume of the container. So it is not going to be now the volume of the container which is going to be the volume of the gas. It would be the volume of the container minus the volume of the solid block of wood, which will give you the volume of the gas, because the gas is going to spread in only that volume which is given to it. When you put some block, that area is gone. Okay, so please do remember these things when we are doing the problem solving. The volume of the gas is going to be the volume of the container. Now the next thing is that the gases, they are homogeneous. Well, what do we mean over here is that they have a similar composition throughout the whole volume. For example, when we talk about air, so air is a homogeneous mixture. There are many gases present throughout the one portion of air, that is nitrogen, oxygen, and many other gases. So all of them, they are uniformly spread over the whole volume that is over there, right? So they are going to be spread throughout the volume that is there, and that is going to be a similar composition. It is not that in some portion of air you will be having more oxygen and in some portion it is going to be less of oxygen. The next we have is compressibility. Now we have discussed that the molecules, they are far away from each other, and when they are far away from each other, well, we can apply some pressure on the gas and squeeze those molecules together because they are already large spaces. So they can just squeeze in and occupy some less space as well. So this is going to be the property of compressibility, squeezing of the molecules close to each other when we apply pressure. And how are we going to apply pressure? For example, we have a container which is a 2-liter container, and that is fitted with a piston. So what we will be doing is that we will be pushing the piston downwards, and when we push the piston downwards, the volume of the container is going to decrease, and the gas is going to occupy now a less volume because of the phenomenon of compressibility. Okay. The next we have is random motion. So the particles in the gaseous phase, they are having the maximum thermal energy. When they have the maximum thermal energy, they have the maximum kinetic energy. So the particles, they are in constant random zigzag motion in all directions. And one of the important applications of this random motion of the gases is that the gases, they exert pressure equally in all directions, right? So for example, if you're trying to inflate a balloon, you will be seeing that the balloon is getting inflated in all directions. It is not that it is getting inflated in some direction, in other direction it is not getting inflated. You will getting a spherical sort of a balloon because the gas particles, they are exerting pressure in all directions. The next we have is diffusion. So the gases, they can diffuse, or you can say they are mixing with each other freely due to the free motion of the particles. The next we have is density. So you all know that the gas molecules, they are far away from each other. So what is density? Density is mass per unit volume. And when we talk about mass, more is going to be the number of molecules per unit volume. More is going to be the mass per unit volume. And the gas particles, because they are going to be less in number per unit volume when we compare it with the solids and liquids. Therefore, what we will be having for the density is that the gases, they will be having low density because of the large empty spaces present between the molecules, right? So these are briefly the characteristic properties of all the gases, but there are going to be certain properties which are not going to be seen for all the gases. So let us see some specific properties of the gases as well. So the gas specific properties are going to be those properties which are going to depend upon the nature of the gas, and therefore they will be changing from one gas to another. For example, odor of the gases, they can be different. H2, O2, N2, they are all odorless, whereas ammonia, sulfur dioxide, chlorine, they have characteristic odors. And then we have color of the gases, H2, O2, N2. Again, these are all colorless gases, whereas NO2, this is brown colored gas. Then we have the solubility of the gases. Ammonia, HCl, they are extremely soluble in water, whereas H2 and O2, they are sparingly soluble in water. And can you tell me why they are so? Well, if you remember our discussion on the intermolecular forces, then you will be able to answer this. What is ammonia? Well, ammonia is having a covalent bond between nitrogen and hydrogen. So when we are going to put this into water, what is going to happen? This is going to be what type of interaction? It is going to be a hydrogen bonding taking place. Therefore, ammonia, this is soluble in water. And when we talk about HCl, this is a polar covalent compound. Again, this is going to be soluble in water, whereas H2 and O2, they are non-polar covalent compounds. So they are going to be sparingly soluble. And O2, even in the small concentration, when it is going to be soluble in water, this is going to be very significant for the aquatic life. So the sparingly soluble oxygen is the one which those aquatic organisms, they are breathing in. Okay, so these are some gas specific properties which are going to vary from one gas to another. Now, the next thing is that the behavior of the gases, when we are talking about, they are going to be governed by the same general laws because they have same general characteristic properties. And these same general laws, these are called as the gas laws, which we are going to discuss in detail. And these gas laws, they were discovered by various scientists as a result of their experimental studies. And we will be discussing them in the next lecture one by one. And these laws, they give the relationship between the measurable properties of gases. So now what I'm going to discuss in this lecture is going to be these measurable properties of gases. What are these measurable properties of gases? How do we measure these properties of the gases is what we will be learning, and this is again going to be very important for your problem solving when we come up to the questions related to the gas laws. Okay, so please understand everything very well. So the measurable properties of the gases, they include mass, volume, pressure and temperature. And when we consider mass over volume, that is going to give us density. So this can become one more measurable property of the gas, but that is essentially again because when we have the mass and volume, so this is going to be a derived quantity. So the four main measurable properties of the gas, this is going to be mass, volume, pressure and temperature. And it is based on their relationship that we have the gas laws that you have to study in detail in this course. Okay, so let us quickly see about these important facts about these measurable properties of gas, because these are going to be again very important when you're going to do your problem solving. Okay, so first we have is mass. And when we talk about the mass of a gas, how are we going to calculate the mass of a gas? Well, we have one container in which we have taken some gas, and then we empty out that container. And what we will be doing in both the cases is that in the first case, first let's measure the weight of the container plus the gas, call it W1 kg, and in the other we will be removing that gas, evacuating that gas, and we will be weighing the empty container again. Let that be W2 kg. So what is going to be the weight of the gas? It is going to be W1 minus W2 kg. Okay, now as far as kg is concerned, so mass is expressed in kg because this is the SI unit. But generally what we will be doing is we will try to express this in grams, because the mass in grams divided by the molar mass which we have in grams, this will give us the number of moles of the gas. So this is again a very important relationship when we are going to do the various gas laws. Although you have already discussed this, you already know how to calculate the number of moles, but this is going to be very important. Okay, so the number of moles of a gas, if we denote that by N, this is going to be equal to the mass in grams of the gas divided by the molar mass of the gas, and both of these, they are going to be in grams. And 1 gram, you all know, that is going to be 1 by 1000 of a kg, because 1 kg is 1000 grams. So the next property of the gases, this is going to be volume that can be measured. So this is the space occupied by a gas, and therefore now you understand that the volume of the gas, this is going to be the volume of its container. If it is a 1 liter container, the volume of the gas is going to be 1 liter. If it is a 2 liter container, the volume is also going to be 2 liter. Now when we talk about volume, the most important things that you have to understand over here are certain interconversions which are going to be required for your problem solving. So let us quickly see those interconversions, and please, you are supposed to remember them all. They are going to be really very important. Most of the things you already must be knowing, but in case you do not, please remember that you have to learn these. Okay, so the volume, the SI unit is going to be cubic meter, which we write as meter cube, where 1 meter cube, this is going to be the volume of a cube of length 1 meter. The next what you have to learn as the interconversions are that 1 meter cube, this is equal to 10 to the power 3 decimeter cube. So 1 meter, this is equal to 10 decimeter. So 1 meter cube becomes 10 to the power 3 decimeter cube. And 1 decimeter is equal to 10 centimeter, or 1 meter is equal to 100 centimeters. So 1 meter cube becomes 10 power 6 centimeter cube, and this is also equal to 10 to the power 3 liter. So now this is something that is going to be very important, the relationship between meter cube and liter. Okay, so these are the things which are generally asked in your questions. You will be given the volume in liter and you have to express your answer somewhat in meter cube or decimeter cube. So these are the relations which are going to be very important. So 1 meter cube, this is equal to 10 to the power 3 liters or 1000 liters. Okay, so 10 power 3 is 1000, or you can say that 10 power 3 decimeter cube, this is equal to 10 power 3 liters. So this means 1 decimeter cube, this is going to be equal to 1 liter. So the next things that you learn over here is 1 liter, this is equal to 1 decimeter cube. 1 liter is equal to 1000 ml. So 1 decimeter cube is also equal to 1000 ml, and this is also going to be equal to 1000 centimeter cube. Because here also you have learned 10 power 3 decimeter cube, this is equal to 10 power 6 centimeter cube. So from here also you can, I hope, understand that 1 decimeter cube is equal to 1000 centimeter cube. So these are the relations which are going to be very important for you people. You should know them very well. Okay. The next after volume we have is pressure. Now, first of all, what you have to understand is how the gas is exerting pressure. So the gas, you know that this is going to consist of the gas molecules, and the gas molecules, they have thermal energy. Thermal energy is the measure of the kinetic energy of the molecules. So this means that if the gas molecules, they are having thermal energy, they are having high kinetic energy, and when they are having high kinetic energy, the particles, they are moving at a great speed. When they are moving with this great speed, they are going to collide with the walls of the container in which they are kept. So what is going to happen is, when they will be colliding is, they are going to bang on to the wall of the container with some force. So force divided by unit area of the container is going to give us what? It is going to give us pressure. So the force exerted due to the collisions of the gas molecules on the container wall per unit area of the container is going to be the pressure, right? So this is how the gas is going to exert pressure. The next thing is, what you have to understand over here is that we have a very important term related to pressure, and that term is atmospheric pressure. The atmosphere, the air around us, this is exerting pressure. How is this exerting pressure now? Well, again, the air around us, that is consisting of so many gases, nitrogen, oxygen, and so many others. So again, we have gas molecules. Again, gas molecules, they are going to collide with various other substances, and those various substances, they are going to feel the pressure of the collision of the gases, right? So air around us, that is also exerting pressure. Now, this atmospheric pressure, this can be measured. How do we measure it? Well, we have an apparatus called as Mercury Barometer, which is going to measure the atmospheric pressure. How do we do it? Well, we take a glass tube which is closed at one end. We fill it with mercury and invert it into a container of mercury. Okay, so why do we take mercury over here? We will be discussing that also, but just remember that we have taken a closed tube which has filled mercury and we have put it into inverted it into a container of mercury. Right now, this container of mercury over here, you can see that we have surrounding air. So air, it is consisting of nitrogen gas, oxygen gas. So these gas molecules, they are going to come and strike the surface of the liquid. And when they are going to strike it, they are going to exert some pressure, and that pressure is downwards. Right? So this is the pressure of the atmosphere on the surface of the liquid. As a result, what is going to happen? Because the pressure from this side is high, so the liquid is going to try to move somewhere where the pressure is going to be less. So as a result, what it will be doing is, it will start rising in this tube which was inverted into the container. Right? So as a result, the height of mercury, this is going to increase. So we will be getting some height of mercury, and that point where that becomes stable, that is going to be the length or the height of the mercury column, and this is going to be a measure of the atmospheric pressure. right? I hope you are getting me. So the length we are going to note, the height of the column we are going to note, and this is going to give us the measure of the atmospheric pressure. How do we do that? Now let us see a mathematical derivation how we are measuring from the height of the mercury column pressure. So we have pressure is equal to force over area, and force is what? This is mass into acceleration. So mass into acceleration over area. Now this acceleration, this is because of gravity, right? So the particles, they are exerting pressure in the downward direction. So this is acceleration due to gravity. So we have mg over a. Now mass is going to be the mass of mercury in the tube. G is again, as I told you, acceleration due to gravity. And if now rho is the density of mercury. Okay, so rho is the density of mercury. What we have mass is equal to is rho into V. So density into volume, because density was mass over volume. So we can say that M is equal to rho into A into H. So what is A into H? Volume is equal to area into the height. So area is going to be, A is going to be the area of cross section of the tube, and H is going to be the height of the mercury column. So from this, what we can put in the values we will be getting is P is equal to mg over A. This becomes rho into V into G over A, and putting the value of V also, we got rho into A into H over G divided by A. So AA is going to cancel out. We will be getting rho HG. Right? So we have the pressure is equal to density of mercury into height of the mercury column and into G, that is the acceleration due to gravity. So density of mercury, which you will be remembering over here, is that 30.56 gram per centimeter cube. Okay, so G value you already know. So what you require to find out the pressure is the height of the mercury column, and if we find it out at sea level, what we get is the height of this mercury column is going to come up to 760 mm. Okay, so this is what we get as the height, and if we get that, what we will be getting as the pressure is going to be 1 atmospheric pressure. So 1 atmospheric pressure, this is going to be equal to 760 mm of this mercury column at sea level. So we will be putting up the definition also on the next slide. Now, one thing more over here, what you will remember is that why we are using mercury. So mercury, first of all, we are using it because it is a non-volatile liquid. It is not going to evaporate. Okay. The other thing over here is that the density of mercury is very high. Supposedly, if we had taken water over here instead of mercury, you know what is going to be the height of the mercury column equal to 1 atmospheric pressure? That of the water column, it would be 10 meters. So that is going to be too much of a height for calculation purposes of the atmospheric pressure. It is going to be really tough for somebody to go up to that height and see the level. Okay, and comparing to water, mercury, it is just 760 mm. So you can understand, because of the high density of mercury, the rise in the mercury column, that is going to be less as compared to water. So that is why we are not using water, we are using mercury in measuring of the atmospheric pressure. So now let us quickly put this into words as well. Mercury, why it is used as a liquid in the barometer. This is one of the frequently asked questions in the subjective examination, and we here believe that we have to prepare you for all types of examination, be it subjective examination, be it competitive examination. We are trying to give you the best content possible for that. So why is mercury used as a liquid in the barometer? The first thing is going to be that mercury, this is almost non-volatile at ordinary temperature. The pressure exerted by the vapors above the column is going to be negligible. If it would have been some vapors present above the column, this would have also exerted pressure on mercury, and therefore the readings for the atmospheric pressure, that would have been incorrect. So mercury being almost non-volatile at ordinary temperature, this is giving us the accurate readings for the atmospheric pressure. Next we have is the height of the liquid in the column. This is going to be inversely proportional to density. More is going to be the density of the liquid, shorter is going to be the column. And if it is shorter, well, this is going to be of a convenient height which we can read very easily. So mercury, which is very dense, this supports of a column of a convenient height, and we all know 1 atmospheric pressure is going to be equal to how much? It is going to be 760 mm, which is quite a short column and very convenient for us to read, whereas for water, which was going up to 10 meters height for 1 atmospheric pressure, you can imagine putting up ladders and ladders and going up to that height to measure the atmospheric pressure. Next we have is that the height of the mercury column, this also varies with temperature because the density is going to vary with temperature, and also it is going to vary with altitude because the force of the gravity is going to vary with altitude. So with mercury in the barometer, we are able to see the pressure changes with temperature as well as altitude. So these are few of the advantages we have of using mercury in the barometer. Now, one more advantage you can say is that for ordinary laboratory work, atmosphere, which is also one of the important units of pressure, you will be seeing the questions generally will be having atmospheres written as the unit of pressure for the various numericals, but for ordinary laboratory work, atmosphere, this is going to be a huge unit of pressure, and what we will be using is only mm of mercury. And here what you will remember is that the pressure exerted by 1 tall of mercury column at 0 degrees Celsius, this is equal to 1 torr. Okay, so the pressure exerted by 1 mercury height in the liquid column, this is going to be equal to 1 torr, and this 1 torr, this is coming from the name of the scientist who invented the barometer, Torricelli. Okay, so Torricelli and torr, 1 torr equal to pressure exerted by 1 of mercury at 0 degrees Celsius. So the next thing is the units of pressure. So now let us learn a few important things here as well, which are going to be very important for you. So the first thing, please remember that the pressure of the atmosphere, this changes on day-to-day basis and the same altitude also. So same altitude, you're not going to get the same atmospheric pressure as well. It is going to change with the weather conditions, the temperature of that place as well. So the next thing you will be remembering is that the pressure, this changes with altitude as well. As the altitude is going to increase, the pressure is going to decrease. And why is it going to be so? Well, it is going to be so because as the atmospheric pressure is going to decrease, fewer molecules, they will have enough kinetic energy to move away from the Earth's gravity. And when there are fewer number of molecules, the air is going to be thin, the pressure is going to decrease, right? So the next thing is that therefore we should quantify what is 1 atmospheric pressure. So the standard pressure or the atmospheric pressure, this is going to be the pressure that will support a column of mercury to a height of 76 centimeter at 0 degrees Celsius and sea level. Fine. And what is the relation of now 1 atmosphere that you have already learned to the height of mercury? So 1 atmosphere, this is equal to 76 centimeter of mercury or 760 of mercury, and this is what we call a 760 torr. So torr is a unit of pressure which is going to be equal to 760 of mercury. This is going to be equal to 1 atmosphere. The SI unit of pressure, this is Pascal, which is the pressure exerted with a force of 1 Newton on 1 meter square. So we say pressure is equal to force upon area. The SI unit for force is Newton. The SI unit for area is going to be meter square. So 1 Newton per 1 meter square is going to give us 1 Pascal. Fine. The next we have is that 1 Pascal, this is equal to 1 Newton meter minus 2, and this is equal to 1 kg meter minus 1 second minus 1. So nothing I have put, just the values of Newton into the values of mass into acceleration. Okay. The next we have is that Pascal, being a very small unit, the pressure is also expressed in bars such that 1 bar is equal to 100 kilopascals, that means 10 to the power 5 pascals. 1 atmosphere, this is equal to 1.01325 bar, which is going to be therefore equal to 1.01325 into 10 power 5 pascals, which is going to be equal to 101.325 kilopascal, or 1 bar we can say this is going to be equal to 0.987 atmosphere. So these are the values which you will be requiring for the interconversions. Okay, so please do remember them, keep on writing them again and again so that you learn them by heart. They are going to be really very helpful. So now that we have learned how we are going to measure the atmospheric pressure with the help of the Mercury Barometer, let us also learn how we are going to measure the pressure of a gas in a closed vessel. And here the apparatus, what we call as the manometer. Now the manometer, this is going to be similar to the barometer in principle. The only difference is that the barometer, this will be measuring the atmospheric pressure, whereas manometer, this will be measuring the pressure of a gas in a closed vessel. So as far as the principle is concerned, it is going to be similar way. The gas is now going to exert some pressure on the mercury column, whereas in the case of the barometer, it was the atmospheric air which was exerting pressure on mercury. Okay, so let us see the apparatus. We have taken a gas in a enclosed vessel. This we call as the bomb, and this is going to be fitted to a U-shaped glass tube filled with mercury. Now this U-shaped glass tube, this can be closed at this end, or it can be open as well. If it is going to be closed, we call it as a closed end manometer. If it is going to be open, we call this as a open end manometer. So let us first understand how we measure the pressure of gas in a closed end manometer. So we have a gas over here in the bomb. This is going to have some pressure exerted on the mercury column, right? So it is going to push the mercury downwards in this descending part of the U-tube, and it will keep on pushing it downwards till the pressure of the gas becomes equal to the hydrostatic pressure. And what is hydrostatic pressure? This is the pressure exerted by the fluid. So the pressure of the gas, this has to become equal to the pressure of the fluid, that is the hydrostatic pressure. So mercury will be pushed downwards in this part, and it will be pushed up in this part. Okay, so as a result, we will be seeing a difference in the height of the mercury column. So this we mark as H, and the pressure of the gas, this is going to be equal to H rho G. The difference in the height of the two columns in the ascending and the descending part of the U-tube multiplied by the density of mercury multiplied by the acceleration due to gravity. Right? So this is how we are going to measure the pressure of the gas in a closed end manometer. Next, we move on to the open end manometer. Now, in the open end manometer, the only difference is that this U-tube, this was open at this end. As a result of this, height of the mercury, this is going to depend upon the pressure of the gas, but it will also depend upon the pressure of the atmosphere. So it is going to depend upon both of them. And here we will be having two possibilities now. The pressure of the atmosphere, this can be greater than the pressure of the gas. The pressure of the atmosphere, this can be less than the pressure of the gas. When the pressure of the atmosphere, this is greater than that of the gas, what will happen? It is going to be this end where the mercury is going to be pushed downwards. So it will be rising high in this end, which is closer to the gas side, right? So what are we going to see is that the pressure of the gas, this will be equal to pressure of the atmosphere minus H rho G, where H is going to be the difference in the height. Okay. And in the other side, you can see if the pressure of the gas is going to be more than the pressure of the atmosphere, it is going to be that the gas is going to push the mercury downwards, right? So when it is going to be pushing the mercury downwards, what we will be having is that the pressure of the gas, this will be equal to the pressure of the atmosphere plus H rho G. Okay. So what you will be remembering over here is that if the atmosphere is pushing with much force, it is going to be atmospheric pressure minus H rho G, and if the pressure of the gas is more, then at that time height of Mercury is going to be more towards the open end. So that is going to be the difference over here. Okay, so P gas is equal to P atmosphere plus H rho g, and P gas is equal to P atmosphere minus H rho g. So this is how we measure the pressure of a gas in a closed vessel with the closed end manometer and the open ended manometer. So next we have is temperature, and this is something that you have been studying from your junior classes as well. So this is going to be just a quick recap. So temperature, this measures the degree of hotness of an object, and it is indicative of the randomness of the motion of the particles of a gas. More is going to be the temperature, more is going to be kinetic energy of the gas, more is going to be the kinetic energy, more is going to be the randomness of the motion of the particles of a gas. So this we've already discussed in thermal energy as well. And the temperature, we measure this with the help of a thermometer. The gases, they expand on rise of temperature. So this is also something that you know, that when the temperature is going to increase, the kinetic energy increases, the particles, they are going to move farther away from each other. So gases, they expand on the rise of temperature. And the SI unit for temperature is going to be Kelvin. The other units are degree Celsius and degree Fahrenheit, and the relationship between them is going to be Kelvin. This is equal to 0 degrees Celsius plus 273.15, which we generally take as approximately to be 273. Okay, so Kelvin is equal to 0 degrees Celsius plus 273, or degree Celsius is going to be equal to K minus 273.15, and the relationship between degree Celsius and degree Fahrenheit, that also you have been learning from your junior classes. Degree Celsius, this is equal to 5 by 9 into degree Fahrenheit minus 32. And one more thing, it is practically impossible to cool a gas to 0 Kelvin, which is absolute zero, as all motion ceases at that temperature. So zero kinetic energy, this is not possible. Something that we will be talking again in upcoming lectures. But just remember, this is going to be very important for you. Now, one thing more before I conclude this lecture is going to be related to the composition of the gases, and this is again going to be very helpful and important for you people, that if we have a mixture of non-reacting gases. So remember one thing, that the gases, they should be non-reacting. If they are reacting, this principle what I'm going to discuss over here, this is not going to be applicable. So if we have a mixture of non-reacting gases, the amount of the constituent gases, they can be expressed in number of moles and mole fraction of each gas. So if we have supposedly a mixture of gases A, B and C, the mole fraction of A, which is going to be denoted by XA, this is going to be equal to Na over Na plus Nb plus Nc. So Na is going to be the number of moles of gas A, and B is going to be the number of moles of gas B, and C is going to be the number of moles of gas C. So we have the mole fraction of A being equal to the number of moles of A divided by the total number of moles of all the gases, right? And mole fraction of B, which is denoted by XB, that will be equal to number of moles of gas B divided by the total number of moles of all the gases. And again, mole fraction of C, this is going to be equal to XC, and this is going to be equal to the number of moles of C divided by the total number of moles. And now XA plus XB plus XC is going to be equal to 1. Okay, so this is something which is going to be again very helpful for you for your problem solving. So that would be all for this lecture, and in the next lecture we would be talking about the gas laws. Again, something that is going to be really very important for you people, so please do not miss the coming up lectures. And for that, you have not to do much. You have to simply subscribe to the channel, click on the bell icon so that you get a notification the moment we put up the new lecture for you. If you have any doubts, feel free, mail them us at h2ochemistry@gmail.com. You can join us on the Facebook page of the channel also by the same name, H2O Chemistry. You can put your doubts in the comment section as well. If you've liked the lecture, please do click on the like link before leaving. Thank you and have a nice day. God bless you.